Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is sort of what I'll be going through is a bunch of different case studies we did using one particular technique and talk about how well it worked for different applications. So where this really fits in is with the workload evaluation framework and building these performance models that can later be used by the director to make efficient decisions. So at a high level, our goal is that, given the diversity of systems today and the complexity of the components that make them up, we want to be able to answer these what-if performance questions to say, what if my workload changes, tomorrow suddenly I have a spike? Can I predict how my system will react to that spike? Also, let's say I want to change my system's configuration, right? How is that going to impact the performance of my system given the workload that I expect? And what if they change simultaneously? So to look for motivating scenarios here, I want to be able to figure out what jobs are good to schedule together in terms of workload management, what the ideal configuration is for a system so that I can optimize multiple performance metrics simultaneously, not just performance, but maybe also energy efficiency. And also, can I predict this sort of scaling behavior? So suddenly, if my website gets very high demand, gets very popular, can I predict the reaction of my system when suddenly you have to scale up?
I have a question already. These all seem like they're not part of the reference architecture of the RAD lab.
Okay, so they kind of tie in that you can look at various components, right? So the first one, obviously, you want to figure out this resource contention for the database. So if you have different apps with different types of workloads, you can look at how they will interact and maybe, which apps to co-schedule on, to interact with the same database, if you can overlap that and such.
So it's not SCADs?
It can be SCADs.
That's not your example.
That's not my example, though. We haven't tried this on SCADs yet.
Everyone is going to, accept, every piece of the RAD lab toolkit all at once.
Okay.
Right? They're not all going to drink the SCAD's Kool-Aid at, the first minute that they get anything.
Right. Okay, so I've kind of briefly talked about the motivation. So I'll spend a few slides talking about the context from a machine learning perspective, and then look at 3 specific case studies. One is for a parallel database, how well we did with performance prediction. And then on a multi-core system running a variety of motifs that you care about, you want to be able to optimize the performance of these different building blocks that make up applications. So we use the same technique for that purpose. And then more of a work in progress is to look at Mapreduce workloads, how I can characterize them and try to do performance prediction there as well. Oh, I went backwards. Okay, so simplistically speaking, you have a system, you have workloads that go into it, and then you observe certain behavior, whether it's performance or resource utilization of that workload or whatnot. What we want to be able to do is replace this or, be able to emulate this with a statistical model. So there are various ways to do this. So essentially, if you want to find relationships between the workloads and the behavior, you can construct models manually looking at the specific components of the system. If you understand it well, you can build a queuing model, for instance. You can also construct these models automatically using various statistical techniques. So we will specifically be looking at correlation analysis in this talk. So before we even get there, essentially there are 2 challenges that we need to address, right? First of all, even given a technique that we have at hand, how do we specifically cater it to the problem that we want to solve? And second of all, we have all the systems data, right? You can observe the workload traces as well as, the resource utilization traces. How do you map these traces, the data that you have, into these multidimensional vectors, which make it more amenable to actually applying these statistical algorithms? So to answer the first question, basically we're looking at correlation analysis. In a nutshell, what that does is if you have, let's say your workload is the X and the behavior features are Y, right? So for each request, you have a point on the X space and a corresponding point on the Y space, right? The location of these points, with respect to both of these aspects, may be entirely different. And what the correlation analysis lets you do is find this, colocality across the projected map so that these scattered purple points on both sides end up in similar locations once you do the projections. So this is pretty much the technique that we apply in the rest of the talk. And more specifically, we use Kernel Canonical Correlation Analysis, where this was actually a technique that was developed at Berkeley a couple years ago. And what this gives you is the ability to use kernel functions to describe the similarity of the data points with respect to multiple axes simultaneously. So you get these nice neighborhoods and the clustering effect in addition to the dimensionality reduction. Okay. So the first case study we look at is leveraging this technique to do performance prediction in a parallel database. This was joint work with folks at HP Labs that was recently presented at ICDE. So the problem here is on these large decision support databases, what you really have is a variety of queries that you want to run on really large scales of data in range of terabytes or petabytes. So what ends up happening is you can't really gauge whether a query will take a very long amount of time or will run within an order of milliseconds. And that makes it difficult to do things like workload management, system sizing to see what the right configuration is, how many nodes you want, how big your parallel database should be, and also things like capacity planning, right? So essentially our goal is to try to facilitate these three tasks. So in a nutshell, we want to use a single model to simultaneously predict the performance of new workloads given previously observed workloads. And we have a set of constraints that we want to operate with, right? First of all, we want to make sure that our predictions are solely based on information we have without actually running the queries, right? So this isn't like a query progress indicator where I can look at feedback of actually partially running the query to see, to estimate my finish time. Second of all, we want to be able to predict multiple resource characteristics, not just how long the query will take to execute, but also, how many disk IOs it would take, how many records it will process, and whatnot. And we should be able to predict equally accurately for short-running queries as well as the long-running queries. So for our experiments, we ran on HP's NeoView database system. So essentially, in a nutshell, we had the results here are from having 4 CPUs, and you have a fixed amount of memory per CPU and a single disk for each CPU. And so the data we used was based off of the TPC-DS benchmark, where we used the query templates they provided and also took extra effort to create longer running queries because it seemed, we wanted to get that entire skew there with realistic, that represented realistic workloads. So to represent the data essentially for the X, we took features from the query execution plans, right? So the execution plan is pretty much the most information you have about the query without actually running the query. So we extracted things like, what operators were being used in the plan and how many times did each operator get used and how many estimated rows did each operator have to crunch through as predicted by the query optimizer, right? And for the Ys, basically each time you run a query, you get a set of statistics that are things like, elapsed time, message count, number of bytes transferred, and whatnot, that are specific to each query. So in your training set, you have, both the X as well as the Y, and what you want to do for prediction is predict the Y given the X, right? So for the technique we used, basically the next step was constructing these matrices, which basically described, with respect to the query plan features, how similar is each query in my training set compared to every other query in my training set, right? And similarly, with respect to the performance metrics, how similar is each query with respect to every other query in my training set? Yes, question?
How that you presented earlier around capacity planning and workload management, I don't see that those are immediately derivable from the feature vectors. Are they, or is there still
not
another
from
step?
the feature vectors. So basically, this is a build-up to doing the performance prediction. And once you can predict accurately, you can do a better job with those tasks. Right. So essentially, from these two kernel matrices, which basically describe each training set query with respect to every other training set query, with two views, right, with respect to the plans as well as the performance vectors. We take those in and then feed it into the KCCA algorithm, which in a nutshell just performs a generalized eigenvalue problem where you solve for A and B, which are these bases vectors for the subspaces, such that when I project kx onto A and ky onto B, the projections are maximally correlated, right? So this is sort of a nice intermediate step that we have to work with. So just by looking at this, it's not readily obvious how we can do performance prediction, but essentially there are ways to leverage these mappings. So what we do, we've gone from x and y to kxa and kyb. And so when I get a new query for which I want to predict how it'll perform, I can calculate its projection on kxa, right? And look up its three nearest neighbors on that subspace. And that is just, pure Euclidean distance on that space. Now, by the nature of these projections, I know that the neighborhoods are similar on the right-hand side. So I know that, the same point is likely to have those same three neighbors on kyb. And actually, to do the reverse mapping, so from the projection back to the raw data space, that's not necessarily a trivial task, right? It's not a deterministic reverse mapping. So we just end up using a heuristic where we say, I know the original coordinates of those three neighbors on the raw y space, so I can just look up those coordinates, the performance metrics for those 3 points. And once I have those 3 points there, I can just do a weighted average of their performance metrics to calculate my prediction, right? So essentially, there are various options you can use here. You can vary the number of neighbors. You can vary, how much you weight the neighbors and such. But the simple, 3 neighbors and weighted average with equal weights work pretty well. So how well did we do? Here's a graph of predicted time compared to the actual time the queries took to run. So this is actually on a log-log scale, so we can accommodate the large variance in the run times of the queries in our set. So the green line shows perfect prediction, right? That's, the ideal scenario. And it looks like, with our results, we didn't do too badly. So we actually had a couple of outliers in this particular case. And the nice thing about using the same model for predicting multiple metrics is you can look across the predictions, right? So this is for records used. And you can kind of track these outliers to kind of see, okay, where did we go wrong? How can we use this feedback to improve our predictions, right? So this is just sort of one set of results. I think the booklet includes our ICDE paper, which also looks at an improvement on this approach where I do one pass to kind of cluster the queries or group them by their run times and then have a refined model that's specific to that bucket so that the predictions are much more accurate. So second case study that we applied the same technique to was performance optimization for multi-core. Question?
For case study 1, if you're relying on the statistics output by the query planner about what each operator is going to touch, that seems like having access to some black box of proprietary technology that can be performing arbitrarily sophisticated, guesses about what's going to be the performance of the query.
Right. So there's sort of two things, right? So you're absolutely right about that. But then, so the query optimizer basically, it outputs a cost, right? Expected cost of a query. And we actually, in the paper, compared how our prediction did to, compared it to the cost that the optimizer predicted. And it turns out that we do a better job with the prediction because the optimizer is sort of written statically, like, it's not something that gets updated after you deploy the system, right? So it doesn't react to what it knows about the workloads. It sort of agnostic to the workload that's actually running on the database. So yes, we are using that information, but I think that the goal is slightly different in that it's okay to use the information because, most databases have a good optimizer to come up with a decent query plan, but when it comes to performance prediction, they don't do a good job, and that's what we're trying to address. Okay, so case study 2 here, kind of switching gears. Basically, we talk about how we can optimize the performance of stencil codes, which is one of these scientific kernels that people care about in the multi-core domain. And this was recent work presented at HotPar last month. So the problem here we're trying to address is there are these various building blocks, motifs, if you will, that people build their applications from. So we want to be able to run each of these motifs efficiently. So when you have a variety of these coupled with a variety of different architectures, multi-core architectures that you want to optimize for, the compilers by themselves don't really do a very good job in performance tuning. So the solution that was proposed by the architecture community is auto-tuning, whereby basically these domain experts identify a set of optimizations and parameters for them that are likely to help your motifs run efficiently on multi-core architectures. And then you would generate various code variants specific to an architecture that would kind of experiment with these knobs, right? But then what you end up with is this large set of parameters that you can tune, and you have to essentially traverse that search space in an intelligent way. So the benefits here are that this technique has been, tried and tested on serial as well as some motifs on parallel machines. It's portable across different generations of architectures. It's also easily scalable. So if I want to tune for dual core versus 4 cores, the actual methodology can be recycled, right? So the problem, though, is when you have a variety of optimizations and several knobs you can tweak for each, the combinatorics is enormous, right? So for these sets of optimizations, we end up with about 40 million possible configurations that you can use, and it's often not clear, which subspace to look at to find the ideal set of configurations. So our goals here were to find the best set of configuration parameters to simultaneously tune for multiple metrics of merit. And this should require as little architecture or domain application domain knowledge, provide actionable suggestions so that we can say, try this configuration rather than try this range of possible values for a setting, right? And we should be able to use a small sample of the space, not exhaustively look through the 40 million data points, possible configurations, but try a small subset. So our experiments here, we used structured grids, stencil codes, if you will. In a nutshell, what they do is nearest neighbor calculation. So this is to solve things like heat equations where basically you update a particular node in this grid based on the values of its 6 neighbors or 26 neighbors, right? And we ran these on both the AMD Barcelona as well as the Intel Cloverton machines, and we tried to evaluate how well we did here. So going back to the machine learning picture, essentially to construct our feature vectors for the X, basically what we can vary are these configuration parameters, right? So we have this large 40 million possible search space. So we just sample from that space, took about 1,500 data points there. And what varies is, what compiler optimizations you use, how much you pad your array, or, how many times and in which dimensions you unroll your loops and such. For the Ys, we can essentially use performance counters to observe, how many cycles it took, how many cache misses there were at various levels of the memory hierarchy. And also we plugged in a power meter to the machine so that we can get these wattage readings and calculate energy efficiency. So then again, the procedure is similar, whereby you compare each configuration feature vector to every other configuration feature vector in your training set, and do the same with respect to the performance metrics, the counter data that you read. And then use KCCA to project KX and KY onto these dimensions of correlation. Now, basically we have to figure out how to leverage these projections to find the optimal configuration. So what we did in going from X and Y using KCCA, we went to KXA and KYB, right? So what I want to do is figure out the best X to maximize Y. So we took the best performing point in our training data set, did the same thing, project it onto KYB, find the neighbors there, and we know that by the nature of the projections, the neighbors will be the same, so that point will be located in the same spot. So basically the projection of the best point here had, similar or things that fell in the same cluster, right? So then when we look up the coordinates of those 3 points in the raw X space, that gives me sort of 3 configuration feature vectors to work with, right? So I can take those 3 configuration vectors, and then basically what I did was do permutations on the various configurations within those 3 vectors that I saw. And what that gave me is a new set of configurations I can try. So I would just run that on the platform and observe the performance and pick the best one, right? Any question?
Yeah. It seems like in general the bar for show. So I believe that this worked very well, but was there any previous technique for solving this kind of problem, this kind of search and
Search, right. So essentially, there is prior work from the performance tuning group at Berkeley that tried to do the same thing, but essentially they were incorporating what they knew specific about each architecture and about each specific application to try to come up with heuristics to say, okay, here's something that'll work well, here's a good blocking strategy, so limit it to that range. But that's, a lot of domain knowledge, and, every time there's a new architecture, they had to sit down, spend time figuring it out again. So the idea here was to see if we can automate it in some way, or at least give them hints on what subset to look at.
But it's just a search problem.
Right. It is a search problem, but then at the same time, just varying one knob, like turning it in one direction, doesn't give you a continuous performance improvement, right? There are lots of interdependencies across the various optimizations that kind of make it more difficult.
Comparison point to like black box things like stochastic gradient or to hill climbing.
Okay, so
with restarts.
Right. So hill climbing is something we haven't tried yet, but it is something that we plan to. One issue that is with hill climbing is that you can easily get stuck into these like local minima, right? And so that would be a problem in this case because, essentially when you look at your data, you would easily get stuck in these ruts where you have one special case that gives you particularly good or particularly bad performance, but nothing surrounding it gives you, anything close to that, right? So we're trying to subvert that in some sense. But you're right, we should be comparing our results to hill climbing to see, how much better or worse we did. Agreed. Okay, so these are our results. Essentially, there are lots of things here. So first of all, we looked at a 7-point stencil and a 27-point stencil. These are just like, 2 instances of stencil codes to have a comparison. The various techniques we compare with, so the pink bar here shows, if I had no optimizations turned on. This is just running the stencil code naively without trying to tune it, right? So the orange bar here shows an expert optimized configuration, how it performs. And this is basically, one of our recently graduated students spent, basically his thesis was on how to tune performance on various scientific kernels on a handful of architectures. So he came up with a bunch of heuristics you can use. And so these were the results from his heuristics. So we also looked at, when we randomly sample our space of 40 million configurations, what the best performing point was in our random training data set. Then we just permuted the top 3 performing ones in our training data set to see how well that performed. And the red bar finally shows our technique and how well it worked. So an important point here is that the red bar sort of has the benefits of the random sampling as well as just a genetic permutation on the training data. But then in addition, it has this nice dimensionality reduction and in neighborhood forming effects. So On the 7-point stencil here, we performed, it was about 2% better than the expert optimized configuration for the 7-point stencil. On the 27-point stencil, I believe we performed within 1%, but didn't quite hit the best mark that the expert was able to get, because the padding, array padding size that our configuration came up with wasn't quite as effective as the experts. To look at the results on the Cloverton, basically on the 7-point stencil, we were hitting a bandwidth limit, so we couldn't really extract too much more performance at all. So, but on the 27-point stencil, we outperformed the expert optimized configuration by about 13%. So comparing another metric, energy efficiency, here we have similar results to performance. Obviously, the two are proportional. But there are cases where, for instance, if you're using voltage scaling, you would expect different results, right? You can vary the priorities to make it better for efficiency or performance, and you can look at those results as well, which is part of our future work. So when you look at the auto-tuning time, actually, so to do an exhaustive search, you have these 40 million configurations. It takes about 80 milliseconds per trial, and at 5 trials per configuration, it could take you up to 6 months to explore the entire search space. So the expert optimized heuristic, essentially he was additively, so fixing an order for ordering for the different optimizations, and then exhaustively exploring along one line, fixing the value, and then adding the other optimizations. So the time it took for him to come up with the ordering is not something you can quantify, because there's lots of domain knowledge, both application as well as architecture domain knowledge that went into that. But once you get down to just the heuristics, it would take about 4 minutes. Our technique, so training the data took about 10 minutes, and then building the model is the most expensive part here, but this was done on my laptop, and you can obviously make it more parallel and optimize it further. So that took about 90 minutes. And then to actually evaluate the genetic algorithm, it took about less than 2 minutes, adding to about 2 hours compared to the 6 months to exhaustively explore it. So currently we're looking at other kernels, not just stencils, but also sparse matrices and whatnot, to see if there's just something simplistic about stencils that makes it easier for us to tune, or is it actually an approach that we can try on other motifs. And we're looking at newer platforms as well, to look at, for instance, simultaneous multi-threading, and to see if it's equally predictable, or is it something that makes things more difficult to predict. So moving on to the third case study here, we would like to apply the same methodology to characterizing Mapreduce workloads and trying to predict their performance as well. So the problem here is that we have a very diverse set of workloads that people look at. And it's very difficult to answer, given a Mapreduce job, what's the optimal number of machines to run it on? And also, given the current state of the cluster, should I run my job now, or just wait 5 minutes till another heavy-duty job ends so that I can run it more quickly? So from a machine learning standpoint, what I want to be able to do is characterize the jobs based on their resource requirements, not just how long they take to run, but are they CPU bound, memory bound, IO bound? So if I want to co-schedule jobs, what is the best combination, right? And I want to be able to optimize for data, maximize the data locality and minimize resource contention as well. Also, this issue of scaling comes up quite often, to say, today I'm running with a smaller amount of data, so I can run on 4 nodes, and that's fine. But tomorrow, if I want to run the same workload because there's more data and scale it up, how well will I do? Or is the scaling linear? Most likely not. What are the bottlenecks, right? And part of an effort going on at the Rad Lab with a bunch of other grad students is trying to come up with a Mapreduce benchmark, so that any of the techniques that we develop, we can validate it on something that's realistic and representative. So this is very much a work in progress. So if you're at the retreat next month, we will definitely have some this month. Oh, right, end of this month. If you're at the retreat, we'll have fresh results. So essentially what we've learned so far is that the behavioral signature of each job is very different, not only based on what type of job it is, like whether it's a sort or a grep, but more specifically what input parameters you choose, right? So in a document, if you're grepping in Wikipedia, for instance, for the word the versus for, you know, an arbitrary specific term like parameters, right? Your performance will be very different because of the popularity of the use of the word. And one thing we noticed is that the map performance tends to be pretty much linear with respect to the number of nodes, but when you get to the reduce step, you have increasing amounts of complexity because of the communication patterns across the different nodes. So far we've been trying to identify useful representative features to include in our modeling. So we have the usual suspects about the configurations of the nodes, as well as, you know, trying to capture different jobs. So one thing we thought about was, if I want to run on 100 nodes, if I can build a micro benchmark by running the same job on a subset of the data on 1, 5, and 10 nodes, can I use that curve to tell me something about the job and compare it to the other jobs, right? So the way we plan to use this is, you know, we have the job descriptor vector using the configuration as well as the job-specific regression curves. And for the Ys, we can easily collect the Ganglia metrics for each of the nodes in the cluster to look at aggregate resource utilization and communication costs and such. Yeah?
I've never heard of this Ganglia statistics before. Could you say a little bit about it?
So Ganglia is basically a monitoring tool, right? So you can instrument, you can basically collect things like CPU utilization. If you think of like IOstat, right, whatever it gives you, those are the metrics that we really care about at this point for performing our workload characterization. So then, you know, building the kernel functions obviously will be specific to what features we use and whatnot. So more immediate action items for which we hope to have results by the end of the month are, so for Hive queries, right? So the format of this is very similar to the SQL queries. And so there are these plans that it has for different stages of the Mapreduce jobs. So we can leverage those to construct the feature vectors, right? So that should be a pretty straightforward mapping to the parallel database scenario earlier on. For the non-Hive, for some of these recurring jobs, like cron job type of batch queries, we would like to be able to say, you know, okay, I've run this job 5 times this month. Here's how it performed. Based on what I know from those instances, can I say something about whether it's worth running that query right now or waiting till tonight when no one else is using the cluster, right? So, and obviously we've been putting in a lot of effort into this Hadoop benchmark. We have a handful of actual production data sets that we've been looking at for Mapreduce jobs. And we'd really appreciate your input and feedback based on your experiences with real workloads on Dryad. So, and also obviously what are sort of the complex problems that you face with when it comes to sort of scaling these jobs? What are, you know, specific job types, like what stages become very challenging to figure out the resource requirements for? And also when you have heterogeneous clusters, how do you really account for that, right, in your modeling? If you have any advice or input on that, that would be great. We'd really appreciate it. Thank you. Yeah?
Yeah, so SNT is, of course, a very mixed bag. Mm-hmm. And quite often, I mean, it depends on who you buy them from, but if you buy a popular SNT processor mm-hmm. from a big company, you might discover that the resources are insufficient to fully exploit both of the threads. You may find yourself in a situation where a heterogeneous workload or even different choices for the 2 threads will result in more performance than making a uniform choice across those 2 threads.
Okay.
And it's just, I mean, it's very sensitive to whether you have enough bandwidth in rank prediction. I mean, there's
right.
a list, right?
Right.
A whole list of properties that these microarchitectures have, and you know, you get a different set of results from something like Bulldozer than you get from Laramie, which is
right.
a pretty much flat thing, to mm-hmm. Something else. I mean, it's a real mix.
Okay.
So just a word of caution about trying to come up with the best allocation of
Right.
blocking factors and so on to an SMT machine.
Okay, thanks. That's very valuable. And actually, so one of the things is definitely per kernel we can come up with a pretty good set of optimizations, but I think the problem is more complex when you try to look at multiple kernels, which is more typical in real applications, right? So a good configuration for kernel A and a good configuration for kernel B might not be symmetric, and how to optimize for the combination of both of them. I think because we can look at large search spaces here, and we can just basically increase the search space when we tack on more kernels and try to achieve it in that way, rather than understanding more of the deep workings of the kernel interactions. Mm-hmm.
Done anything looking at the simultaneous scheduling of MapReduce jobs, or how to pipeline them to best balance utilization and completion time?
That's a good point. So the one thing we've looked at actually just in the last week was purely the shuffle step performance, right? So that seems to be a bottleneck, especially when you have multiple jobs running together, right? Which one sort of takes the cake in dominating the resources required there? So, but as for specific scheduling, there's more work that's done by some of our other grad students in the RAD lab. Matej Zaharia and Andy Konwinski. So I can point you to their recent work if you'd like on scheduling. I'm not sure if it's in the booklet or no?
Just submitted.
Just submitted? Okay, right. So, yeah.
Maybe similar thing. I didn't quite understand when you said on the Mapreduce, what exactly are you optimizing? You said it may be better to wait for the evening to run job. So how is it better to wait?
Right, so it's essentially, how well your job performs is also partly a function of what else is running on the cluster simultaneously, right? It's unlikely that your job will have exclusive access to all the nodes that you proportion to it. Often you end up sharing the nodes across multiple jobs.
So you want to optimize how fast job will finish, even if it means you delay when you start it. So from the user perspective, it's always better to submit it sooner.
From the user perspective, yes, but then for things like these sort of data analytics type of jobs, there's no immediate response time hard constraints, right? So you're just calculating statistics on a regular basis, and those can actually they're lower priority, so they can wait. And in some sense, it might be better for them to wait rather than run it now and choke up the current jobs and the resources there.
So it seems like the model you have in mind that you can find those times when clusters are not loaded and
Right. That's absolutely, that's essentially what we're trying to do, right? If we can wait to a time when the cluster is not loaded, that would be nice, but there might be cases where, whatever is available now is more than enough for what I need to run. So then there's no point in waiting.
yeah. So maybe it is unusual, but for whatever reason our clusters are never not loaded. They're always oversubscribed.
Right.
So I wonder what kind of optimization you can do. That's what we get money for, right? We utilize them more than 100%. So what is the best strategy then?
Well, we'll have to investigate and find out. So if you have these... Sorry?
By the end of this month?
Well, no, so essentially it's a matter of, whatever we're trying to do reflects the workload that we have access to right now, right? And so essentially if you have more sort of critical workloads running continuously on these clusters, then they would have very different requirements, and we'd love to hear about that and see what kinds of jobs those are and what kind of requirements they have.
Well, I'm not sure what kind of jobs is so important, and it's more to the point. I think it's more interesting, not to go for easy task of say, well, let's figure out when it's an absolutely safe time to do the job. But it's more interesting to say, well, under hard constraints, when you don't have those things, what are the, and this is similar to the scheduling question.
Okay.
What is the best thing you can do when you're oversubscribed?
Right. Okay.
I'm curious to see what kind of sampling sampling density is required to build an accurate model, and how does your model accuracy degrade as you have fewer and fewer samples?
Okay.
So if your search space is 40 million different parameters,
Right.
different possible configurations, what kind of,
How much you have to go to get an acceptable, right. So actually we did some experiments there to look at, if I vary my training set, started with as low as 100 and went up to, I believe 2,000 or so. So it grows for a while and then tends to plateau. So beyond, like 14 or 15. Right, that was out of the 40 million. So it turned out and also these systems have sort of real limits on how much performance I can get, right? So, I mean, basically based on what resources are available, which resource you'll choke on first really depends on the system architecture, right? And so one of the earlier grad students actually came up with this roofline model that tells you exactly that, to say, when are you going to be bandwidth limited, when are you going to have a different bottleneck. So when we have those upper bounds, we can kind of decide how good do I need to be before I stop trying. Right?
But how many, it was like hundreds was the needed curve?
It was, so 1400 was what we ended up using, right? So that was the knee of the curve. Beyond that, it was pretty much plateauing and marginal gains.
Okay. My name is Kristal, and I'd like to present this work on characterizing Web 2.0 workloads. And this is a work that I've been doing with Archana along with a couple of other grad students in the Rad Lab. And again, here, the overall view of the Rad Lab system architecture. Again, this work fits into building models of the various applications we're considering. So our motivation here is that Web 2.0 applications are very attractive in many ways, and a lot of that has to do with the fact that they allow users to contribute various content, and they also allow for users to interact with each other. So they can keep in touch with various things that are going on in their communities. And these things that make the Web 2.0 applications more interesting than their predecessors in Web 1.0 also make them, their workloads harder to characterize. So we'd like to be able to analyze the workloads that we observe for Web 2.0 applications to find similarities within those workloads. And we'd also like to be able to leverage that assessment of similarity to do predictions of behavior due to changes in the workload. So one example that was pointed out to me by through a conversation I recently had with an engineer from Facebook was that they might want to assess the impact on their system due to kind of promoting one aspect of their website and thereby shifting the distribution of their workload. So this is definitely of interest to many software as a service providers. Also, sometimes we're interested in more than just knowing the response time that will be delivered. We'd also like to know how the resources are being taxed in the system. So we'd like to know, due to this spike in in performance is due to one of our resources becoming a bottleneck. So again, following the format of the case studies that Archana just described, what we'd like to do here is develop a model using machine learning that will allow us to link the system's workload as well as its behavior, its performance, and its resource utilization. And so that model is useful for understanding better the workload that we observe, and also for providing a foundation for actually doing prediction. So the Web 2.0 application that we looked at, we're fortunate in the Rad Lab, as Armando mentioned earlier, that we have some people working on a calendar-based social networking Web 2.0 benchmark called Cloudstone. And we're able to use this by deploying it on EC2, and it consists of several components. So I'm going to go through the components and just talk about what we extract from each of the components and how that goes into our analysis. And this analysis is also a work in progress, so I definitely would value your feedback as well. So first, the load generator is Markovian. So it goes between various tasks that users might want to do, such as creating events, attending events, etc. And each request is issued depending on what was issued at the previous time step. And what we have in this table here is a list of the various requests that are actually issued by the workload generator. Then we have the front end, which consists of both the Nginx reverse proxy and also the HA proxy load balancer. So from Nginx, we extract the performance monitor, or the resource utilization monitors shown here. And what we do to extract that information is we have a daemon that runs on this machine, and every 1 second, it will dump a reading from these monitors to a file. So then at the end of the execution, we'll just download all those files into a centralized location. So then from the HA proxy machine, in addition to the resource utilization monitors, we also collect the HA proxy log. And this serves as a rich source of information for request-related metrics, such as from the URI, we can actually determine the request type according to the table that I showed a couple of slides ago. We can also determine the response time that request observed and the HTTP return code. So then from the Rails server, we can also obtain the production log. And this, again, has per request features such as the queries that will be issued as a result of the particular request, and also the tables and columns that it'll be touching in the database due to that request. And that's going to vary based on the parameters to the request as well as the request type. And again, we want to get those resource utilization monitors. And similarly for the database tier. So just to kind of confirm our intuition that just knowing the request type wasn't enough for accurate prediction, I did some analysis of the variability that we saw within request types. So what we have here is just a display of the various statistics for each request type's response time distribution. So we can see from these that what we would like is a very peaked distribution, like for requests 1, 10, and 12. For most of our requests, we actually see quite a bit of variability. So this is an interesting point about Web 2.0, because in Web 1.0, there were some request type-based systems that were very successful at predicting various metrics of the workload just by having the request type. But those actually have been shown to break down for Web 2.0. And this variability is a pretty strong indicator of why those techniques are breaking down. Because we can see that even though a request type might be the same across various aspects of the workload, we might have very different queries that are generated based on the URI. So, and just to zoom in, we have here just the histograms for a couple of the request types that we saw on the previous slide. And we see, again, that while what we would like is a very peak distribution, we actually see quite a diffuse response time variation within the request. So just knowing the request type isn't going to provide us enough information to do reliable characterization of the workload. So in order to actually, as Archana mentioned, for using machine learning algorithms, we have to choose our algorithm, and then we have to convert our problem instance into input to that algorithm. So a very common input to machine learning algorithms is feature vectors. So I just want to go through how we create the feature vectors for input to our KCCA algorithm. So the workload for our application can be thought of as a stream of requests, where here by the color of the squiggle, I mean to indicate the type of the request. So we just observe this stream. And rather than considering individual requests, we choose to consider windows into which several requests fall. And the reason for this is, as I've indicated by these blue arrows, we are going to take periodic measurements of the resources that are being utilized throughout the system. So rather than trying to attribute those measurements to individual requests through some sort of regression, we chose to just consider the interval And this also seemed to make sense because often we care more about the load to an application, to a web application, than we care about the individual requests that are being issued. And also, requests to a web application are almost probably never going to be issued in isolation. So it really doesn't, it's not too necessary to consider that fine grain of a representation. So what I've indicated over here on the left is that, as Wei mentioned, there's a technique, bag of words from document analysis and information retrieval, in which we like to indicate how many of each type is present in that interval. So we just go through, and from the HA proxy log, we're able to identify the type of each request, and we create a distribution over those request types to represent each interval. And we also take the features that we obtain from the Rails log, such as the queries that are generated by each request, which we can know without actually running the request. And that serves to represent the X representation. So just to reiterate, we kind of divide all the metrics that we collect from throughout the tiers of the application into two views, the X and the Y. So X are things that we can know without actually running the workload, the things that just describe what requests are being offered. Whereas the Y are things that we have to actually run the workload to know, such as the resource utilization. And the reason we want to have this clean separation is because then we can do a prediction, because in the predictive scenario, you would only have the X. So we've talked about how we have our system to which requests are offered and from which we can observe behavior. And we've also talked about how we can develop our X and Y feature vectors to comprise a two-view data set. So the next thing, we'll just briefly reiterate what Archana mentioned about how to use KCCA to find the correlations within that data set. So our data set here is very naturally represented in two views because what we're building toward is prediction. And in a predictive scenario, you would only have that X view. So KCCA is very applicable here. We use a Gaussian kernel to compare the requests to each other. And what that figure is showing at the bottom of the slide is that, so we take the X, the list of X vectors, which are the representations of each interval. We compare each vector to all the other vectors via the kernel. And then we record in KX a measure of the similarity of each vector to each other vector. And then we project those large matrices onto the dimensions that capture the correlation between the two views. And so this also is very fitting for our scenario because we want to have multidimensional X and Y. We want to be able to express a variety of things about the workload, and we also want to be able to measure more than one metric. So for our evaluation, we were able to deploy Cloudstone on EC2. We had 1,000 intervals as our training set, 100 for tests. And then, so where we are right now is we kind of have done some analysis to observe the locality that's provided by this model. And we're kind of working toward the prediction results. So to echo some of my colleagues, I hope to have some prediction results at the retreat. So this should serve as additional motivation to attend the retreat. So what I wanted to show here is kind of a motivation for why we can't just compare an incoming workload to some of the X views that we've seen in the past in order to get a prediction for its resource utilization. So I just chose a random 0.500 out of this points 1 to 1,000 that comprised my training set. And I indicated the labels of some of the metrics I was considering on the axes. So these yellow triangles are the three nearest neighbors with respect to X. So I took the X representation of 0.500 and found within X its most similar X vectors. Okay, and then this is a bit confusing, but I'm showing the resource utilization of those three input vectors. And so you can see that they're kind of distant from that one. However, when we take the 3 nearest neighbors with respect to y, they're very similar. So we see that just because the requests looked similar in their input representation, that wasn't enough to determine what would be a similarly behaving interval. So to look at what we get from KCCA, here on the left I've shown the projection of the x. Oh, okay. So on the left I have the projection of the x, and on the y the projection of on the right the projection of the y, and we can see that they are very visually similar. And I just took that same 0.500, and it had the same nearest neighbors in the 2 plots. So this is just kind of motivating that just looking at the raw data isn't going to give us the similarity that we have to have for prediction. But as Archana was talking about with just the, since we find the dimensions of correlation onto which to project the data, we can actually get better neighborhoods among the 2 views of the data so that we can leverage that for prediction. So the prediction results are forthcoming at the retreat. So just some final thoughts. Web 2.0 apps are definitely of interest, and predicting their behavior due to changes in workload would be very helpful for many service providers. And some of the case studies that Archana presented give strong evidence that this is a compelling solution for this sort of problem. And some of the things that I'll be working on in the near future is just some of the feature engineering, including taking those queries that we can infer to be generated from the request and getting the query plans so that we can use that as part of the X representation. Also just kind of tweaking the interval length. So we used a 1 second interval in this case study so far because it made sense that most of the requests were contained within that 1 second because the requests were so short. So, but I'm definitely interested in what kind of interval would make sense to you that have more experience with the real systems. And also, we'd like to add more machines because we know that's more interesting. So some things I'd like to solicit your feedback on are some other features that might be appropriate and might help for the prediction. Also, I mean, we have so many possible metrics that we are gathering from every machine, as well as just IOStat, VMstat, NetStat. And I'm curious about what metrics we should focus on, like what would be most of interest if we can predict those reliably. And assuming that this model would yield accurate prediction, what would be the most compelling use cases for it? I mentioned earlier the case of promoting a new aspect of the website and shifting the distribution of workload, but I'm wondering if there are other anecdotes that might show the usefulness of this model. Also, so when we're actually trying to predict, that would involve constructing a new X vector. So I'm wondering what kind of knobs you would like to turn. Is it just the shifting of the types of requests, or are you willing to turn some other knobs about the queries that would be generated by those requests? So thank you very much, and I'm very interested to hear your feedback.
I'd like if somebody else gave some feedback.
But you're doing so well.
Well, I was just wondering about whether or not, I don't know the answer to this one relative to what people who really do this for a living would say, but it seems to me the amount of variability in a query is another interesting thing to try to predict. It's a little bit, I mean, it's all over the place, of course, and the sorts of queries that are highly variable are the kinds of queries you might want to over-provision or you're into QoS, for example, or whatever. I mean, it's an interesting subclass.
Okay.
I mean, just a thought.
Mm-hmm.
So, I mean, that sounds like one version of feedback on what could one use this for, right? If you find some set of queries that doesn't appear to categorize nicely, no matter how you slice it, then maybe the right answer is just know how many of those you're going to get and over-provision for that fraction of
Right, for example.
Yeah, that's a good insight.
But if you go back to one of the earlier talks, I mean, some of these queries are very data dependent. You know, if you start scheduling an event, and it turns out there are a lot of entries in the database associated with it, it's going to take a longer time. There's the one where you find out there's not much associated with it. And so looking just at the query isn't going to necessarily categorize it very well.
So you're saying that that query might have performed very differently in the past than it will now just because of the data has changed in the...
Well, the type of query, I mean, I assume you're looking at the type of query rather than the specific parameters to the query. And so
you can actually look at the parameters as features. There's the trick is how much you try to featureize, right? So if you're looking at, let's say,
I know, but if you look at this, but you know, going to the social event, then that type of website is that if you look at the specific event, that's going to quickly go out of date. It's the date that the event passes, and you have new events to schedule.
So it's unlikely
and so
the
predictive
value will be
value
the
is not going to
same.
be useful.
So you'd have the same predicate, but then the specific value you're searching over, for instance, would be very different. And unlikely to get a hit based on their training data.
okay, so and I guess that's another thing to think about then is what aspects of the way that you're featureizing it might turn out to be data dependent, which implicitly might mean time dependent, given the kind of app you're using as a test case.
Sure.
I'm curious if it makes sense to kind of up-level up and look at the clusters of queries. For example, if you have an Ajax app, usually it's not a single query, it's a combination of queries, and the performance of the app is not limited to just one query.
The cluster of queries like
There are
that are
some
happening
relation-
at the same time, or?
Kind of go to the scenario level. I don't know.
Okay.
So you asked, what are useful metrics? What are metrics that other people care about? I thought that was a very good question. The answer that I would have to it is that all the scenarios that you want to enable really are one step removed from performance metrics. There are things like, is it safe to add capacity or remove capacity? And I think one of the things I'd be very interested in seeing is that this intermediate step of being able to predict these performance metrics is a key enabler of that, as opposed to trying to map more directly from something like this feature vector that you have to some other feature space, which is like time to add or remove a machine, right? Total number of machines in the system. And so that's actually something that I would think is a big potential contribution of this work, is showing that this is a really important intermediate representation.
Okay.
So let me make sure I understood that. Instead of necessarily trying to predict, sort of low-level performance metrics directly, try to find correlations to operational parameters that you would use to make decisions like that, to make provisioning decisions or reallocation decisions or something.
Yes, or show that, in fact, if you try and run, 5 algorithms on that problem, that it doesn't work as well as having this intermediate representation of predicting the individual CPU network usage.
So based on my
okay.
predictions,
So
now I can decide if I should add
So I'm not
machines
saying,
or...
yeah, I'm not saying I know which one is the better approach. I'm saying I would love to see proof that this is the better approach or not.
So is that kind of in the same line of her comment about how maybe comments about the actual anomalies that were found could be then an intermediate step toward actually making correlations between the performance impacts, and so that's kind of...
I don't remember that. Maybe I wasn't paying attention
Oh,
to that
okay.
comment was made.
But yeah, I mean, so like Wei had presented some anomalies that he had found in the HDFS logs, and then the comment was made that maybe that could be leveraged to really diagnose what the performance impact of those things were. So it's kind of a good use case of that.
I think it might even be simpler to summarize what you're saying is, if your goal is to answer these operational questions, one thing you could do is start from the low-level metrics trying to answer the question directly, but probably a better or more effective thing you could do was start from the low-level metrics, get this, and then use this as the representation to help answer the questions.
And I think it gives you a very nice kind of compelling, here's what I improve on, right?
Right.
Another question I have after listening to you, Peter, and Archana is around the importance of transients. So in Peter's work around, I add a machine, I remove a machine. There are these constants that get stuck in around like, oh, because machines take about a minute to warm up, I know that after I've done this, I wait a minute before measuring, and then I can measure. And so that's very much kind of a magic number that gets put in, and it's different for different applications. And I see this today in practice that these magic numbers are all over the place, but this is one where I don't see this work yet making that particular magic number also go away.
So one way how you could measure what the number is that
Yeah.
assume that you have a model that you know it's correct for the steady state.
Right.
You take that model, you apply it right after you add a machine. If the first X minutes are transient, then the model will not work well in the first X minutes, right?
So,
and you can compute some common kind of a deviation of the observed values, and then after that transient goes away, the model should start working again correctly.
So if you had graphs showing this today,
And so-
I would have been very impressed with
Okay,
it.
so I actually did that with this, right? So I fit the model from say a couple hours of data, then I fit it just to the first 20-second interval, the next 20-second interval, and the third 20-second interval, and computed the deviation of prediction from the model, right?
Yeah, I mean, it's like getting the step response of the dynamic
Right,
system,
right.
basically.
And so
I'm not saying it's
The observation
impossible,
I
but
made is sort of the negative step response looks.
Why, yeah, why isn't it the same as the positive step response?
Yeah, well, why is it not symmetric? I think I know,
Why is it
but I
not
mean, it's worth looking
Yeah,
at.
that was a good question.
So I'm not saying that this is a terribly demanding additional goal, but it's one of these things like saying models need to be retrained on the fly that I think can actually influence the problem formulation significantly. The burden to have to say, have your model training step be robust enough that it's okay to evaluate it constantly in real time on your production data.
I think it gets a lot more complicated when we start talking about scaling up and down scats. When you're actually adding a machine means you have to now copy 10 gigabytes of data with that machine, right? And so now the transient could be half
Much
an hour,
bigger.
right?
Yes.
And
Yes.
And the other way could be good too, so.
right,
Because you
Yep.
have to say this data is ongoing.
right.
Right.
Other questions, comments?
You didn't
Oh, yeah, I actually have more.
Still have time.
So the other one was around confidence intervals, in that, we brought up with Peter's talk just that confidence intervals seem like they might be very nice to expose in order to provide more data for making these decisions, and that also seems like a very nice thing to tackle. And my last thing was actually just about KCCA, which is that I feel like KCCA can be justified either as its most accurate technique that we have for this kind of problem, but in that case I'd like to see more comparisons with other potential techniques, or it can be justified as it's the most principled technique, which I'm also very open to being convinced of, but every time you say 3 nearest neighbors, I feel like it's not yet meeting the bar of the most principled technique.
Because 3 seems arbitrary, or?
It's 3, well, why not something like, take the mean along that subspace of all the other data points, or the weighted mean.
So asking as a non-machine learning person, suppose that we said, it's 3 nearest neighbors, and here's why. We tried 2, that didn't work well. We tried 4, we tried 5, it added a lot of complexity, but it only improved the answer. So in other words, would an empirical validation, how much would an empirical validation persuade you?
Well, that's then just emphasizing that it's the most accurate technique, which then I'd be more interested in seeing kind of comparisons to other techniques. Because today I didn't see any comparisons to other techniques of KCCA. I felt like the emphasis was entirely on this approach philosophically fits this problem domain well.
Although there is some more of that in the papers, to be fair. There are some especially in the first of the papers, which was on the database test case.
So that actually looks at the design decisions specifically for KCCA as well as compares to other algorithms, non-KCCA. So yes, of course that is very empirical. We love to see if there is a way to kind of figure out algorithmically what the right number of neighbors is. So if you have any thoughts on that, or
Also, philosophically, I'm curious about that question. So obviously, here's one approach, right? There's n other approaches. We can't evaluate it against all n other approaches.
Right.
But in practice, we found that most people who have that kind of question mean one of 2 things. One possibility is, I'm familiar with state-of-the-art technique X, How does it compare to that?
Right.
And the other flavor is, I've heard of people doing much simpler things that don't require you to know much machine learning. Why didn't you try a simpler thing?
Right.
Which flavor is closest to the one that you're asking about?
I'm probably more curious about the first, but they're both good questions, right? And they both seem very addressable. They're just, and I'd also like to see that experiment.
Well, the problem with I was a little worried with nobody would bring this up, because I had personally guaranteed that every time we give a presentation, someone's going to ask that question. And we're batting 1,000 for 20 presentations. That question always comes up. So one of the things, but it's usually in a machine learning skeptical audience. So one thing we're working on is the one-page kind of tax on using machine learning in systems. The one page. For those of you who know machine learning, skip this page. For those of you who don't, might want to read this page thing. We have to argue kind of philosophically why machine learning is a good thing. But then, for what algorithm seems natural, that's a tough one. Because even in presentations where Archana shows a few, they'll ask about, what about these others?
What about this, the third thing that's not very...
And even though in theory you should be able to just, replace this and plug in another one, it's not always that easy, right? You can't just switch the algorithm.
Right, it could be a lot.
And it's a lot of work.
Also, there's kind of a broad range between, the simplest and KCCA, right? So then there's just like what level they're convincing along that range. Right?
So if you try something that's too simple, people say, well, that's not fair. You're doing this brain dead simple thing. Of course, yours is going to be better.
Sure.
So it's, but we're not pushing back. I mean, we agree that a lot of people ask a similar question, and we're still grappling with what's the most effective way to answer the question.
But we're going to try. I think we're going to try the principled argument in the write-up. Why this makes sense.
Yeah.
But apparently, in trying to push back to understand this, part of it is that the phrase is machine learning.
Yeah.
Because we didn't claim anything, it's just some words. The words machine learning make it sound, mystical, right? That it'll do something beyond with what we claim it will, because if it was called statistics.
I know what you mean.
Yeah.
It was called more sophisticated statistics.
Then that wouldn't bring up this other aura, but even though we didn't say anything about it, we used that word, and then people think we're claiming something that we didn't mean to claim. So it's I don't know, it's cultural or psychological or something.
We're also, or at least I'm in favor of trying what I see as a kind of more offensive approach, which is when people say, why do you have to try this exotic algorithm, to respond, well, it's not really that exotic. You may be ignorant of it, but in fact, it's been widely used in biology and supervision people, so if you don't know it, you should go read Wikipedia, but the algorithm is not that exotic.
Ignorance is not that pejorative.
So it's actually so when it comes to like being exotic, I think it's more that with something like linear regression, it's relatively easy to have a mental model of okay, if I perturb one data point, I know what's going to happen. This it won't have an outsized influence, whereas the three nearest neighbor property makes you think one data point can make a big difference, right? It's not bounded by the number of data points. It doesn't. That influence of one data point doesn't degrade as the number of data points grows.
Actually,
and so it's also that scariness.
So in machine learning, in a more machine learning oriented audience, I think you don't have to spend as much time justifying the principledness of k-nearest neighbors, because people have already had a lot of exposure to it, and there has been a lot of work done to show that, in fact, k-nearest neighbors being one of the simplest classification algorithms actually works surprisingly well compared to some sophisticated classifiers. And so the k-nearest neighbors actually is a really simple one, and the idea of like reducing down to a reasonable Euclidean space and then doing k-nearest neighbors, that just makes sense too. So people would think that is principle, but that comes from this kind of background knowledge about what has already been done, which is
Did the recording capture everything Alice just said?
Not very clearly.
Yeah, so maybe I can just reiterate. Alice just mentioned that k-nearest neighbors is also a very well-known technique throughout machine learning. And so although it seems arbitrary to just use three nearest neighbors, that's a very well-known classification and approach. So maybe what we should have done is also kind of justify k-nearest neighbors, and maybe that would have kind of rounded things out.
I don't think we've done that.
We haven't, no. Thank you for that feedback. That's really helpful. Yeah.
And lots of people also talk about, how do you select K? And yeah, indeed, it is very sensitive to outliers. So, but that's also a problem that people know about, and it's like, well, you just deal with it. You know, yeah, have more data.
Yeah, I mean, I think a lot of machine learning algorithms have some notion of parameter, right? It's like none of them will just work out of the box. We have to kind of choose some things about it, and that's one thing about k-nearest neighbors. But I think also, like, Archana found in some of her database experiments that really adding more neighbors just gave like a marginal improvement again, right?
Sometimes there's no improvement at all, and you're better off just sticking to the ones that you know are closest and ignore everyone else who's further away.
Yeah.
Okay. Would that be interesting in knowing, you know, how dense the space has to be populated
Right.
before it breaks, right? Clearly, if the points are far away, you're not going to get a good prediction, right?
That's a good point, actually. So basically, you know, if your projections aren't very, you know, if they're scattered, then it's one thing to say, okay, my test data point falls within that realm of, you know, things I've already seen. If the test data point is further away from everything I've seen, then obviously my confidence will be lower and my accuracy will be lower.
Like, luckily, if you do an experiment where you say you have 1,000 data points, you just do the cross-validation where you remove one,
Right,
and then you just test on that, you might get much better accuracy than if you say split it in half.
right, exactly.
Right? And so that would be more interesting experiment to see.
I mean, but prediction in general kind of relies on the fact that you've seen things before that
Right.
are similar to what you've seen now.
My issue with this is like I have no sense of how close, when you're doing the prediction for unknown workloads, here because you're going into this new space, I don't know how close you really are, right?
In the
When-
actual
like when-
space.
Right.
Right,
And like
I see
in the
what you
models that I'm using in the director, you know, I'm usually looking at the workload, number of machines, I can clearly visualize this is the data that I've seen, and I know exactly how far away from that subspace I'm trying to predict, right?
So you want to see
Right.
like how different is what we're seeing now from what we've
Right,
seen
because I have
before.
no sense at all, right? You know, is it really close? Are you really kind of just interpolating within points that are really
Right,
close?
so
or?
I mean, so the only way we could really define how close they were in the raw space is look at the query structure. So we made a conscious effort to remove templates that we had already seen from
Right.
the training set, right?
Right.
So we used totally different templates for the training and test, but beyond that, you know,
Right.
if they actually do similar things, you can't, I mean, we didn't look for that per se, we didn't capture that.
I mean, do you have any idea of what you would like to see? Like what would be more convincing or?
Not at this point, but we could talk about it.
We should get together at Berkeley and talk.
Yeah.
Come up here and talk.
Yeah. Well, you guys
Thank you.
probably have to
That's
catch
your plane or something, but
Thank you very
much.
much.